Now that we have defined the PCA problem, defined the PCA procedure, and derived the solution for it, let's look at some interpretation for it. More specifically, let's look at the variance of the projection of the training data set, right? So we already computed phi j's for j equals 1 through m, right? We were given these training samples and we did the PCA procedure in it. So to review again, PCA procedure is 3 steps. Step 1, center the data. Step 2, compute the covariance matrix. Step 3, compute the decomposition of this covariance matrix. And from the eigenvectors of the covariance matrix, we get phi j. So this is what we did to the training data. So now let's take a particular phi j. I'm not saying this is 1 or the mth one, some phi j. And let's project each of the data points, the training data, onto this axis provided by phi j. So here's the axis provided by phi j. And for each data point here, I'm computing the projection. So, this value along here is by phi j. And so we're going to have many points here now, each point on this line. And of course, the mean here will be 0. It's easy to see, but let's compute the variance of all of these points. So variance, the sample variance of all these points. The sample variance is 1 over n, that is the average. Well, this is the biased one. We're going to do 1 minus 1 here, but it doesn't matter, is the value minus its mean, right? And so let's look at the mean. The mean is computed as 1 over the sum of all, 1 over n over the sum of all the values, but we already applied the centering procedure to the data set, so the sum here is always 0, so the mean is 0. So that's simple, that goes away. So therefore, the variance of this is simply the sum over that, in which, these are values of a vector squared, so I just separate this as a transpose times itself and rearrange the order once again so that I can see that this middle term here is once again my sample covariance matrix. But we already set these phi j's to be the eigenvectors of this, so this is equal to that, right? Because that's the eigendecomposition of S. So in other words, this is just a number, so this times this is the norm squared. But we already decided this is also, already constrained it to be orthonormal, so meaning the norm is also 1, so this is 1. So the variance of this guy is simply the eigenvalues of your sample covariance matrix.